Welcome to DAR Space. This is gonna blow your mind. Imagine the shoelaces on your favorite pair of sneakers. What's the most important part? You might think it's the lace itself, but think again. It's those tiny plastic or metal tips at the very end, the aglets. Without them, the laces would fray, unravel, and become a useless mess. They protect the main lace, allowing it to do its job day after day. Now what if I told you that deep inside every single one of your cells, your very own genetic code has its own version of these protective tips? This isn't science fiction. It's one of the most elegant and fundamental truths of our biology. It's a story that unfolds on a microscopic scale, a drama of survival happening trillions of times over inside you right now. These biological aglets are called telomeres. They are simple, repetitive sequences of DNA that cap the ends of our chromosomes, which are the tightly wound bundles of our genetic information. Think of your chromosomes as precious encyclopedias containing every instruction needed to build and run you. The telomeres are the sturdy covers on these books. They don't contain any vital information themselves, no recipes for eye color or instructions for making your heart beat. Instead, their job is purely protective. They prevent the crucial pages of your genetic story from getting tattered, torn, or accidentally fused with other encyclopedias, which would be a catastrophic error for the cell. This protection is absolutely vital. Inside the bustling city of your cell, there's a constant process of copying and dividing. Every time a cell replicates to heal a cut, grow new skin, or simply maintain your body, it must make a perfect copy of all its chromosomes. However, the cellular machinery that copies DNA isn't perfect. It has a peculiar quirk. It can't quite copy the very end of a chromosome strand. It's like a photocopier that always leaves a tiny, uncopied margin at the edge of the page. Without telomeres, each time a cell divided, it would lose a little bit of its essential genetic code, a process that would quickly lead to disaster. So nature came up with a brilliant solution. It placed these disposable, non-essential DNA sequences at the ends. With every cell division, it's the telomere that gets a little bit shorter, not the vital genes within. The telomere acts as a sacrificial buffer, bravely taking the hit so that the important genetic information remains intact and undamaged for as long as possible. It's a beautiful, simple, and incredibly effective system. It's the unsung hero of your genome, the silent guardian that ensures the integrity of your very essence, one cell division at a time. This tiny detail is the starting point for one of science's greatest stories about life, aging, and even the dream of immortality. Let's journey back to that copying process. Each time a cell divides, a tiny piece of its telomere cap vanishes. It's a one-way street of shortening. Imagine a long fuse on a firework, burning down a little bit with every spark. At first, the shortening doesn't matter much. The telomeres are long and there's plenty of buffer to spare. The cell continues its life, dividing and functioning just as it should. But this process is relentless. Division after division, the telomeres shrink. Slowly but surely, the protective caps are worn away. This gradual erosion is more than just a mechanical process. It's a biological clock, ticking down the lifespan of the cell. This ticking clock is, in many ways, the molecular heartbeat of aging itself. As we grow from a single cell into a complex organism with trillions of them, and as our bodies repair and renew themselves throughout our lives, our cells are constantly dividing. Each of those divisions is a tick of the clock, a scraped knee, a sunburn, or simply the daily replacement of old cells in your gut. All of these processes shorten the telomeres in the affected tissues. It's a fundamental cost of living, a biological tax paid for the privilege of growth and repair. The vibrant youthful cell with long, healthy telomeres eventually becomes an older cell with shorter, more fragile ones. When the telomeres become critically short, the cell faces a monumental crisis. The protective caps are almost gone. The cell's internal alarm systems, which are designed to detect DNA damage, go haywire. They see the exposed chromosome end not as a normal part of the aging process, but as a dangerous break in the DNA. This triggers a profound change in the cell's behavior. It receives a powerful, irreversible signal to stop dividing forever. It enters a state of retirement, a kind of cellular old age known as senescence. It's not quite dead, but it's no longer contributing to the growth and renewal of the body. A senescent cell is like a retired worker who still hangs around the office. It stops dividing, but it doesn't just sit there quietly. Instead, it starts secreting a cocktail of inflammatory proteins that can cause trouble for its neighbors, contributing to the chronic low-grade inflammation we see in many age-related diseases. As we get older, more and more of these senescent cells accumulate in our tissues. They can compromise tissue function, slow down healing, and are linked to conditions like arthritis, heart disease, and even some forms of dementia. The shortening of our telomeres, therefore, isn't just a sign of aging. It's an active participant in the process. In the 1960s, a brilliant scientist named Leonard Hayflick made a discovery that would forever change how we think about life and death at the cellular level. He was growing human cells in a petri dish and noticed something peculiar. No matter how well he fed them or cared for them, the cells didn't divide forever. They would divide and divide and divide. But then, after a certain point, they would just stop. They would hit an invisible wall. This observation led to a groundbreaking concept now known as the Hayflick limit. It's the fundamental rule that a normal human cell can only divide a finite number of times, typically somewhere between 40 and 60 times, before it enters senescence and stops for good. This limit is directly tied to the length of our telomeres. The 40 to 60 divisions represent the number of ticks on the cellular clock before the telomere fuse burns down to its end. It's a pre-programmed obsolescence built into our very biology. Why would nature do this? It's thought to be a powerful anti-cancer mechanism. A cell that could divide forever would be at a much higher risk of accumulating dangerous mutations that could lead to unchecked growth. The Hayflick limit acts as a safety brake, ensuring that most cells retire before they have a chance to go rogue. It's a trade-off. In exchange for protection against cancer early in life, we accept the inevitability of cellular aging later on. What's fascinating is that this limit isn't universal across the animal kingdom. It's tuned to the lifespan of the species. Human cells might get 40 to 60 divisions, setting our maximum theoretical lifespan at around 125 years. But look at a Galapagos tortoise, an animal that can live for centuries. Its cells can divide over 110 times, giving it a much longer runway before cellular senescence kicks in. On the other end of the spectrum, the cells of a laboratory mouse, with its short 2 to 3 year lifespan, can only divide about 15 times. The Hayflick limit and the rate of telomere shortening seems to be a key dial that nature uses to set the pace of life for different creatures. This raises a mind-bending question. If the Hayflick limit is the lock, is there a key? If our cells are programmed to stop, could they ever be programmed to keep going? This is where the story takes a turn toward the extraordinary. While most of our cells are bound by this rule, there are exceptions. There are certain cells within our own bodies and within the natural world that seem to have found a way to defy the countdown. They possess a secret weapon, an enzyme that can turn back the cellular clock. This discovery opened up a whole new universe of possibilities, blurring the line between aging and immortality. The discovery of the Hayflick limit presented a puzzle. If all our cells have this built-in countdown, how do we exist at all? How does life pass from one generation to the next? The answer lies in a remarkable enzyme called telomerase. If telomeres are the fuse burning down, telomerase is the magical substance that can rebuild it. It's an enzyme that has the unique ability to add the repetitive DNA sequences back onto the ends of chromosomes, effectively lengthening the telomeres. By doing so, it resets the cellular clock, granting the cell a new lease on life and the ability to keep dividing far beyond the normal Hayflick limit. Because of this incredible power, telomerase is often called the Immortality enzyme. It's the closest thing we've found in biology to a veritable fountain of youth. Where is this enzyme active? In most of our somatic or regular body cells, telomerase is turned off or present at very low levels. That's why they age. But in certain special cells, it's switched on and working hard. The most important of these are our reproductive cells, the sperm and egg. This is crucial. For life to be passed on, the next generation must start with a full set of long telomeres. Telomerase ensures that our children don't inherit our own shortened, aged telomeres. Besides reproductive cells, telomerase is also active in embryonic stem cells, the master cells that build the entire body from scratch. These cells need to divide an immense number of times to form a complete organism, a feat that would be impossible if they were constrained by the Hayflick limit. Some adult stem cells, which are responsible for replenishing tissues like our skin, blood, and gut lining throughout our lives, also maintain some telomerase activity. This allows them to persist and keep our bodies regenerating, though usually not enough to completely halt the aging process over a lifetime. It's a carefully regulated system. The delicate balance of telomerase activity is one of nature's most profound acts. Too little, and we age prematurely. Our tissues fail to regenerate, wounds heal slowly, and we become frail. But too much telomerase carries its own profound danger. A cell that can ignore the Hayflick limit and divide forever sounds a lot like a cell with a one-way ticket to becoming cancerous. This duality is the central drama of telomere biology. The very enzyme that holds the promise of extended youth and regeneration is also the key that unlocks one of our most feared diseases. The quest for immortality, it turns out, walks a razor's edge. The ability to divide forever is the hallmark of a cancer cell. While normal cells respect the Hayflick limit and dutifully retire, cancer cells find a way to cheat death. They achieve a twisted, dangerous form of immortality, and their secret weapon is almost always telomerase. It's estimated that a staggering 80 to 90% of all human cancers have figured out how to switch the telomerase gene back on. This is a pivotal moment in the development of a tumor. A precancerous cell might be dividing too quickly, but it's still on a timer. Once it reactivates telomerase, the clock is gone. The safety brake is cut, and the cell is free to multiply indefinitely. This stolen immortality allows a tumor to grow from a small cluster of rogue cells into a life-threatening mass. Each time a cancer cell divides, its telomerase enzyme diligently rebuilds its telomeres, ensuring that its descendants can also continue to multiply without limit. This makes telomerase a tantalizing target for cancer therapy. If we could find a way to specifically shut down the telomerase in cancer cells, we could theoretically reimpose the Hayflick limit on them. We could force them to age and die just like normal cells. It would be like taking away their fountain of youth, leaving them to wither and fade away. But what about the other 10 to 15% of cancers? Some of the most aggressive and difficult to treat cancers, like glioblastoma in the brain or osteosarcoma in the bones, don't use telomerase. For years, this was a deep mystery. How were they maintaining their telomeres and achieving immortality? Scientists discovered they use a completely different, more chaotic method called alternative lengthening of telomeres, or ALT. Instead of rebuilding their telomeres with an enzyme, ALT-positive cancer cells use a messy process of physically swapping DNA from one chromosome to another, using a healthy telomere as a template to patch up a short one. The existence of the ALT pathway highlights the relentless ingenuity of cancer. It shows that if there is a way to overcome a biological barrier, cancer will often find it. This makes the fight against cellular immortality more complex. It's not enough to just target telomerase. We also need to understand and find ways to block this alternative route. The dark side of immortality isn't just about endless life. It's about life that refuses to follow the rules, life that grows at the expense of the whole, and life that will use any trick in the book to keep going. It's a powerful reminder that the secrets of life and death are guarded for very good reasons. The central role of telomerase in cancer has transformed it from a scientific curiosity into one of the most promising targets in modern oncology. Since telomerase is highly active in most cancer cells, but silent in most normal adult cells, it presents a beautiful opportunity. We can design therapies that specifically hunt down and attack cells that are expressing telomerase, leaving healthy cells largely unharmed. This is the guiding principle behind a revolutionary new approach, telomerase-based cancer vaccines. These aren't preventative vaccines like the ones for measles or the flu. They are therapeutic vaccines designed to treat existing cancer. The concept is elegant. The vaccine works by teaching the patient's own immune system to recognize a key component of the telomerase enzyme, a protein called H-TERT. The immune system's T cells, which are like trained soldiers, are shown this H-TERT protein and told, "This is the enemy. Find any cell that is making this and destroy it." Because only the cancer cells are producing large amounts of H-TERT, the immune system is unleashed on a specific and devastating hunt for the tumor, wherever it may be hiding in the body. This approach turns the cancer's greatest strength, its immortality engine, into its greatest weakness. This isn't just a theory, it's already showing promise in clinical trials. A vaccine called UV1, for example, has been tested in patients with advanced melanoma. When combined with other modern cancer treatments called immunotherapy checkpoint inhibitors, which release the brakes on the immune system, the results have been very encouraging. Patients receiving the combination have shown significantly better survival rates. Another vaccine, UCPVax, is being tested in patients with liver cancer, showing that it is safe and can successfully rally the immune system to fight the disease. We are at the dawn of a new era where we can weaponize the body's own defenses against cancer's immortality. These advances represent a monumental shift in our battle against cancer. For decades, our primary weapons were chemotherapy and radiation, blunt instruments that carpet-bombed the body, killing fast-growing cells indiscriminately, both cancerous and healthy. Now, we are developing smart bombs. By targeting the fundamental biology that makes a cancer cell, like its reliance on telomerase, we can create treatments that are not only more effective, but also kinder to the patient. The quest to understand the telomere, which began as a journey into the nature of aging, has given us a powerful new hope in the fight for life. Just when scientists thought they were closing in on the secrets of cellular immortality, a new discovery in 2024 revealed another layer of complexity, particularly for those aggressive cancers that don't use telomerase. Remember the ALT pathway, the chaotic cut-and-paste method used by about 10 to 15% of cancers to lengthen their telomeres? For years, the precise mechanism was a black box. Researchers at Carnegie Mellon University finally pried it open, and what they found was a complete surprise. The key player wasn't a familiar protein, but a tiny molecule with a rather memorable name, SUMO. SUMO, which stands for Small Ubiquitin-like Modifier, acts like a molecular master of ceremonies. In ALT-positive cancer cells, SUMO molecules begin to cluster at the ends of the chromosomes, right at the telomeres. This clustering has a remarkable effect. It acts like a beacon, gathering all the necessary DNA repair proteins into one place. This high concentration of proteins forms what scientists describe as a biomolecular condensate. Think of it like a tiny, self-organizing droplet of liquid forming right on the telomere. Inside this droplet, the frantic DNA swapping and patching of the ALT mechanism can take place efficiently. This discovery was a game-changer. It revealed that the ALT pathway wasn't just a random mess, it was a highly organized, albeit unusual process orchestrated by SUMO. More importantly, it provided a brand new target. The researchers found that if they used drugs to inhibit the action of SUMO, the entire process fell apart. The droplets couldn't form, the repair proteins couldn't gather, and the cancer cells could no longer lengthen their telomeres. The ALT pathway was shut down, and the cancer cells, stripped of their immortality, began to age and die. The growth of these highly aggressive tumors was stopped in its tracks. This breakthrough opens up a completely new therapeutic avenue for some of the deadliest cancers we face. While telomerase inhibitors are promising for the majority of cancers, they are useless against ALT-positive tumors. Now, with the discovery of SUMO's critical role, we have a way to attack these cancers as well. We are moving beyond a one-size-fits-all approach and toward a future of precision medicine, where we can analyze a patient's tumor, determine its specific immortality mechanism, be it telomerase or ALT, and then choose the exact drug designed to shut that pathway down. The SUMO surprise is a powerful testament to the importance of basic research in uncovering the universe's hidden rules. The connection between shortening telomeres and aging is undeniable. As our telomeres get shorter, signs of aging appear. It's a correlation so strong that it's tempting to declare, "Case closed." Telomere shortening is the cause of aging, but science is rarely that simple, and many brilliant minds in the field believe the story is more nuanced. They argue that telomere shortening might not be the root cause of aging, but rather one of the most important and visible symptoms, a biomarker or a tally mark, but not the puppet master pulling all the strings. This has sparked one of the most fascinating debates in modern biology. The evidence for this symptom argument is compelling. Consider the mouse again. Mice have telomeres that are, on average, 5 times longer than human telomeres. If telomere length were the sole determinant of lifespan, you'd expect mice to live far longer than we do. Instead, they live for about 2 to 3 years, while we can live for 80 or more. This paradox suggests that the overall rate of aging is controlled by a much more complex network of factors, and telomere length is just one component. Other processes, like metabolic rate, DNA repair efficiency, and the accumulation of cellular damage, likely play equally, if not more, important roles. Proponents of this view see aging as a multifaceted process, like a car wearing down over time. Telomere shortening is like the odometer tracking the mileage. It's an excellent indicator of how far the car has gone, but it's not the reason the engine is losing compression or the tires are going bald. The real causes are the fundamental wear and tear from oxidation, inflammation, and small unrepaired errors that accumulate throughout the system. In this model, telomeres are part of the story of aging, but not the whole story. They are a crucial chapter, but not the title of the book. So, who is right? The truth likely lies somewhere in the middle. Telomere shortening is probably both a cause and a consequence. It is a direct cause of cellular senescence, which in turn drives many aspects of organismal aging. At the same time, the rate at which telomeres shorten can be influenced by other aging factors, like stress and inflammation, which can accelerate the process. The debate itself is incredibly healthy for science. It pushes researchers to look deeper, to challenge assumptions, and to build a more complete and accurate picture of one of life's most profound mysteries. Whether a cause or a clue, telomeres have undeniably pointed us in the right direction. Our journey into the world of the telomere began with a simple shoelace tip and has taken us to the frontiers of cancer research, the mystery of aging, and the very definition of life itself. The quest to understand this tiny piece of DNA is more than just a scientific endeavor. It's a reflection of a deeply human desire to understand our own limits and perhaps to one day transcend them. The dream of immortality, of cheating death, is as old as our species. But what the science of telomeres teaches us is that immortality is not a simple switch to be flipped. It is a delicate and dangerous balance. Nature has already shown us the price of unchecked immortality: cancer. The very mechanism that could grant our cells eternal life is the same one that fuels our most relentless disease. This duality forces us to ask profound questions. Is a longer life a better life? What would it mean for our society, for our planet, if we could significantly extend our lifespan? The research isn't really about creating immortal humans, it's about creating healthier humans. The goal is not necessarily to extend lifespan, but to extend health span, the period of our lives that we live free from chronic, age-related disease. The story of the telomere is a beautiful illustration of how science works. It's a tale of curiosity, of meticulous observation, of unexpected discoveries like the Hayflick limit and the sumo molecule. It shows us that even the smallest, most obscure components of our biology can hold the keys to understanding the biggest questions. It's a reminder that the universe within us is just as vast and mysterious as the universe outside. Every cell in your body contains a story written over billions of years of evolution, a story of survival, adaptation, and the intricate dance between life and death. As we stand here today, on July 2nd, 2025, we are closer than ever to reading that story and perhaps even editing a few sentences. The therapies being developed today, the cancer vaccines, the sumo inhibitors, are the first practical fruits of this incredible journey. They may not make us immortal, but they may save the lives of millions and allow us to live our finite lives with more health and vitality. The quest for immortality, in the end, may not lead us to eternal life, but it is leading us to a deeper understanding of what it means to be alive, to be finite, and to be human. And that, perhaps, is the most profound discovery of all. Este video estuvo super épico, pero si crees que este estuvo increíble, el video anterior te volará la cabeza. No te lo pierdas, dale click y sigue explorando los misterios de la vida con nosotros. From Darspace until next time.